Hello everybody. So in this video we are going to solve a couple of problems on the YouTube manometer concept, and the problems are all going to be focusing on the same thing, which is using the manometer uh, and applying the concepts that we know about fluid statics, which are the two rules that two points at different heights will have difference in pressure equal rho gh, and 2 points at the same height will have the same pressure. So here, for example, we have a pressurized tank. So this is air that's under pressure, and the pressure is measured by multi-fluid manometer. A multi-fluid manometer is kind of two merged manometers. So you have a manometer that is upward, or the U shape is upward, and here is another manometer with the U shape downward. This is what we call the multi-fluid manometer. The tank is located in a mountain at altitude of 1400 meters, where the atmospheric pressure is 85.6 kilopascal. So this is one given information, that the atmospheric pressure is 85.6 kilopascal. This is one information we are given, and we need to find the air pressure in the tank. We don't know the pressure here. If H1, if this distance is 10 centimeters or 0.1 meter. So this is something we usually see in these kind of problems, that we have the heights put on the diagram, because it's very hard to describe by words. So it's easier to have them drawn on the diagram. So this is H1, which represents this difference in height. And we are given that H2 is 0.2 meters, H3 is 0.35 meters, so we already have these as given information. And we know the density of water to be 1000 kilogram per meter cube. The oil is 850. This is the oil, which is 850 kilograms per meter cube. For mercury, it's which is this fluid, it's 13,600 kilograms per meter cube. So we need to know what is the pressure of the air in this chamber. So for these problems, it's usually we know an information about the pressure at one point, and we need to use this information to get to the other point. So the way we can do this is to go with the manometer fluids from the known part to the unknown part. So the known part is here. We know the pressure, which is the atmospheric pressure, which is 85.6 kilopascal. So we know the pressure here, and we need to pick some points here that we can jump from one to the other. So we can calculate the pressure at one point given the pressure at another point. So we know the pressure here at point 2. The letters A, B, C, D, and E are letters that I put myself on the diagram, because these are the points that we are going to use. So we have here this interface, where we have the bottom line for H2 and H3. I have this at point B, and this the point at the same level on the right side of the YouTube manometer is point A. So I can calculate the pressure at point A given the pressure at point 2. So if I can calculate it using the pressure at point 2, this is my first step, and then let's zoom in more. So if I can calculate this pressure from here, this is going to be my first step, and I know that point A and B are at the same height and at the same fluid, which is mercury. So we can say that pressure at A equals pressure at B. And now if we focus at this interface, we mentioned last time that the pressure on this side and that side are equal, because this is in a state of equilibrium. So we can use the pressure at point B. Now we are looking at it from the oil side. The pressure at point B is can be related to the pressure at point C. We can get a relation between pressure at C and pressure at B using the height H3. Okay, no, I'm sorry. C is at this height. Okay, and I picked this point because I want to get from here to here. So this is the point C is at this height, H2. So we can calculate pressure at C, which is equal to the pressure at point D. So I know the pressure at point D. It's equal to the pressure at point C, and now we can go from the water point from the water side. So the pressure at point D is equal to the pressure at point E, which is a point at the same height in the water. And from here, we can get a relation between the pressure at point 1, which is the air pressure, and the pressure at point E. So this is the plan for the solution. We need to be very careful about the heights because sometimes it confuses, but it should be a very, very systematic approach. So now we can go from points A and B are at the same level, so we can say that PA equals PB, and PB is the atmospheric pressure plus rho GH. Now this is the density of mercury, because this is the fluid we have here, times G times H3. Okay, so that's why I put rho mercury GH3. And I'm going to put them as equations, and I'm not substituting until I reach the end. So this is the pressure at point B, is the atmospheric pressure plus rho mercury GH3. Now the pressure at point C can be got in terms of the pressure at point B. So the pressure at point C is PB. Keep in mind that PA is larger than P2, okay, because PA is at lower at higher depth. Now PB and PC, C is at lower depth, so PC is PB minus rho GH. Okay, so it's PB minus rho oil. Now the yellow fluid is oil minus rho oil GH2. Now this is at height H2. Okay, and now we know PB is P atmospheric plus rho mercury GH3, so we can take this, put it here instead of PB. So this is the equation we are getting. Now we have a formula for PC. Of course, you can substitute with numbers and get the numbers directly at for each pressure, but I think this way, by writing the equations, you are saving a lot of time that you are spending for substitution. Now we know that PC is equal to PD. So PD is the same thing, atmospheric pressure plus rho mercury GH3 minus rho oil GH2, so it's the same thing. And we know that PD is equal to PE, so it's going to have the same value. Now we have a point at this height, and we want to get the relation between the point of water at this height and the point at the surface. So it's going to be the same as what we did here between B and C. So it's going to be P1 minus rho GH. This is PE, or I mean PE equals to P1 plus rho GH. So P1 is PE minus rho GH. Of course, this is rho of water, GH1. So this is the relation between P1 and PE. Okay. And again, we can substitute with PE with all these three terms. So now we have four terms that give a relation between P1 and the atmospheric pressure. Now by substitution, we can find the pressure, which is 129.65 kilopascal. So as I said before, you have the freedom to substitute for each step, or to put them as formulas and substitute one time at the end. It's fine. But the thing that you need to pay attention to is to make sure you put this sign correctly. If it's going to cause some confusion, one thing that you can do is always to write the deeper point in terms of the shallower point. So you put PE equal P1 plus rho GH, and then to rearrange the equation if the signs will cause some confusion. Now we have one other problem to solve here, which is a similar one. It's about a mercury manometer, which shows a differential reading of 0.3. It's a manometer between two containers containing two fluids. This is water and this is oil, and the manometer contains mercury. And the mercury manometer is used to measure the difference in pressure. We are given here an information that the pressure in the pipe A is 30 millimeter mercury vacuum. 30 millimeter mercury vacuum means that it's 30 millimeters below the atmospheric pressure. If you remember, in the beginning of this chapter, we said there is a gauge pressure and the vacuum pressure. This is the vacuum pressure, so it's 30 millimeter mercury below the atmospheric pressure. So it's going to be 730 millimeter mercury absolute. Which is you can use the conversion factor to get it in units of Pascal. We want to calculate the pressure in pipe B if the specific gravity of the oil is 1.25. and given that the heights in the figure, we're given some heights in the figure, the 0.5, 0.15, and 0.3. Again, I put some points, highlighted some points here that would be of interest, so that we can proceed with the calculation. So we know that the oil, we know the oil density, we know the water density is 1000 kilogram per meter cube, the mercury is 13,600 kilograms per meter cube, the same numbers that were given in the previous problem. Now given this information, we can proceed with the solution the same way. We know the pressure at point A and we want to use it to get the pressure at point B. So what we can do is to go from A to C and then from C to D. D is the same point at the same height with the interface on the other side. And we can calculate PC in terms of PA and this height and the density, of course, of water. PD in terms of PC and this height and the density of mercury. PD is equal to PE, and we can get a relation between PE and PF given this height difference, and PF is equal to PB. So it's a very, very simple process. So at point C, the pressure at point C is PA plus rho water G times 0.15. So we can calculate the pressure at point C. Here I did the calculations. So I did both approaches in the two problems. The previous was with the calculations at the last step. Here I did the calculations at each step. Now PD is equal to PC plus rho mercury G times 0.3. So this is the density of mercury, G times 0.3. So we have the pressure at point D. Pressure at point D and pressure at point E are equal. So we know the pressure at point E. And now pressure at point F is PE minus rho oil G times 0.45, which is this total height. So now we have the pressure at point F, which is equal to the pressure at point B, because they both points are at the same height in the same connected fluid. So this is all what we need to do in this problem. There is nothing more we can do here. The point I want to highlight here is that all the problems that we see that contain mercury manometers can be solved the same way. The point is, how do you choose the points? If you look to this problem and to the previous problem, here and here, you would notice that the points that I pick are I pick them so that one of them is an interface, either point B or point D, and the other is another point that is at the same height on the other side of the manometer. So for instance, I have this interface here, and then I have this interface here, and I pick the point that is at the same height on the other side of the manometer. For this side, there is no more interfaces, but there is one interface here. So the point that I picked was D, and the other point that is at the same height on the other side of the manometer. The same for this problem. If you look at the points, this point is D that we picked. It is a point that I can calculate from the point above, or the interface above, and point E is the interface on the other side. So I pick the point that has an interface on the other side, and it is at the same height. So this is, of course, you can pick any other point, but the other points will not be helpful or will make the calculations longer. So to make it easy for you to do the calculations, it's better to follow this approach. I'll stop here, and next time we will discuss some other details about the pressure measuring device. See you then.